All right, I'm gonna get started here. So I extended that homework from last time, and we're in some what I would call challenging material, implicit differentiation. We're trying to apply it to related rates. Those are the two things that I think. And mean value theorem is the other thing that was extended. So I'm happy to chat about some of those problems. If you're one of the folks who are just kind of waiting to do the homework until the last minute, then I would encourage you to start it a little bit sooner, because we have some good discussions in some of my office hours, and those are a good time to work on homework. Anyway, do you guys want to talk about some specific problems? Or are you doing okay on the ones that are due now this evening? One of the things, I'm going to ask you a question on the quiz today related to implicit differentiation. So if there's anything that's not clear about that particular homework, we should look at some of those. Yep.
What I got, including what I put in Wolf alpha, math's completely different, and I couldn't understand this.
Okay, so let's look at that. What was? Do you know what the problem was that you were talking about? Okay, so how can I help? You just want to talk about in general e to the x? I mean, so something like this.
Y was next to the x squared.
Okay. Is this the implicit differentiation one, right? And so then the y is a function of x. Yeah, this is a tricky one. So that when we do d over dx of these things, the right-hand side shouldn't be too bad, right? That's just, and let me maybe just move that over, so, because we're going to need a bunch of room for this, the one on here. But this one is just 1 plus dy dx, right? So that right-hand side shouldn't be too bad. I agree, the one on the left is tricky because it's a chain rule, and it's gonna have a product rule up in the exponent, right? So when we think about the derivative of the exponent, which will come as part of the chain rule, or as part of the chain rule, it's gonna involve the product rule. And so let me know if this looks okay. We can talk about the details if you want, but when we do the chain rule there, the e part stays the same, and then we end up multiplying by the derivative of the inside piece, right? So that would be the chain rule as a whole, and then this is the product rule part. So first part look always looks so messy when I look back at all the things I've noted there, but does it seem okay so far? Yes. So then this part stays the same. And then when we do the product rule, it'll be f prime g plus f, and then g prime is just going to be dy dx. So that's what I think that's what it should look like. Do you recall whatever you looked at said instead? Wolfram alpha or something like that?
I think the end result was that equation plus 1, and then over that equation minus 1. But it with Wolf alpha, it was the 1 first, and then the equation.
So what was Wolfram alpha telling you? The derivative? Was it telling you y prime? Was it telling you? Sorry, let me get rid of this here.
I understand the factoring it out and so equal to y prime, but I still didn't get the right answer.
So what is the goal of this problem? Solve for y prime?
Yeah.
Okay, so let's do that then. So we want to get the y primes on the same side, right? We want to get like this and this. These are the y primes. We want to get them on the same side and then factor it out and divide everything else there, right? So that involves distributing this through there And then we'll have to get them all on the same side. I don't know, maybe the algebra is part of the confusion here, but this is what it would look like. Let me do the intermediate step. I'm just gonna write dy dx as y prime. Hopefully that's all right. And so I think it looks like that. Wish we could just like make this go further. Can I really don't like this whiteboard because I don't need to do that and then it just goes away. So can I like, all right, and I'll have to copy that over, I guess. I think I'm just gonna bring it back up top here, maybe. All right, so this is, let's get all the things. I'm gonna go back up here with it. Let's get the y primes on the same side. So this has got a y prime, and then I'm gonna move the other one over to the other side, right? So I'm putting these two things on the same side, and then we can put these two things on the other side. Right, because we want to get y prime by itself, so I've got the y primes together. And the whole point of doing that is because then you can factor out the y prime. And so let's just pull the y prime out front. And this is where the -1 comes in, maybe, that you were talking about. Right. Remember, this is the whole goal, is getting this by itself. And so now we only have one of them. And so we can just divide that other thing to the other side. And that's the answer. And so yeah, it's like 1 minus that thing and then that thing minus 1. Maybe that's what you're talking about. So that's y prime equals that thing on the right. And that's not written very well, but hopefully you get what I mean. Right. Guys follow that? Any questions online there? Open up the chat here. Seems okay?
I think I just switched the numerator and denominator.
Okay. Also, this is different about it too, right? Looks like this one has this multiplication where the bottom doesn't have that. Anyway, I'll get this posted online if you wanted to look at it, the video later. Other sort of homework questions. That one was definitely a little bit of a tricky one. I'm going to ask you a couple implicit differentiation questions on the quiz this afternoon, but they're going to be more straightforward than this one. They're going to be what I would consider more basic type questions. Yeah. Sure, let's take a look at that one. You say 5? Okay, so this is the kind of, I would describe this as the level of difficulty on the quiz. So we should know how to do this one. Let's take a look at it. Then of course it needs to crash first, and then I need to open it back up. Okay, so y is a function of x, right? So when we do d over dx, like this is just a normal power rule. Oh, thank you. Right, still doing the whiteboard thing. There we go. Okay, so y is a function of x. So this is just a power rule, but this is going to end up being a product rule, right? And this is going to be a chain rule. And this is just a constant rule. So just identifying the rules is obviously the first step there. Does that all seem okay? So when we do the derivative, so I'm going to kind of do a little bit of a shorthand here. D over dx is going to be 6x squared on the first one. The product rule is going to be f prime g plus f g prime. Right, this is the product rule. So that's right. And then the chain rule is going to be bring down the power, subtract 1 off the power. So, you do the power rule, but then you need to multiply by the derivative of the inside piece. And we've seen that one a bunch of times already, right? Anytime you have like y of x raised to a power and you want to differentiate it, we've done this at least, I don't know, 10 times probably so far. You bring down the power, subtract 1 off the power, but then you always multiply by the derivative of the inside, right? This is the chain rule. We've seen that a bunch of times. When it's just an application of the chain rule with a power rule, right? Or maybe a power rule with a chain rule is a better way to say it. So that's what it looks like. And then, then the last part is to solve for the derivative and plug the point in. But I think that's the hardest part. So there are questions about the first part? Philip, all right? Anyone online have a question about that? Nope. Okay, so let me erase this part, this lower part. And, let's just review what we're trying to do. It wants the slope of the curve at 3, 4. So we want to, 1, solve for y prime. And then 2, plug in the point 2, 4, or 3, 4. That's what this is telling us to do. Because the slope of the curve is y prime. And then when we plug a point in, it tells us that specific slope. So maybe the algebra is the part. I don't know. So the confusing part, but it's the same idea. You want to get the y primes on the same side and then factor it out. Right, so let's do that. So here's one of the y primes. Here's the other one. This is an 8y dy dx. All right, and I'm going to get rid of the things that don't have a y prime. Let's see that algebra that just happened there. I'm trying to keep the y primes on the same side. So that's these two things. I'm trying to get rid of the things that are not a y prime, which is those two things. Because what's the next step? We just did this on the last one, right? We got rid of the y primes on one side, we kept them on the other side, and then what do? What's the point of that? To solve for y prime, but how do we do that? There's 2 of them currently on the left side. We're going to factor it out, right? So we pull the dy dx out. We've got x plus 8y left. And this is how we're able to get it by itself, right? Let's throw another page on here. Right, we want to get y prime by itself, and we've just about done it. You just divide that stuff over to the other side. And then we just plug the point in to get the answer. I'll let you finish that, but that's the last step. Right, because when you plug in 3, 4, you'll get the derivative of y with respect to x, so y prime of x, at the point 3, 4. So that'll be the slope of the tangent line. So that'll be your final answer here. And a lot of them, half of them, I actually can't remember, maybe I won't speak, but a lot of them do this kind of thing where it wants you to solve for y prime and then plug the point in. This is definitely one of those problems. What do you think? Does that clarify that one for you? Okay. Other homework questions?
I saw a lot of people ask about whether on Slack their types on there. I didn't really get it, so.
Yeah, so this is the same problem. It's just using slightly different notation, which is part of the reasons I like this one. Because we really need to understand the difference between like y and f of x, right? So I think the key thing in this one is just that instead of using y, they're saying f of x, right? It's just the output. So if it's helpful, you could rewrite this problem as 9 plus 5y plus 4x squared y cubed if you wanted to. Then it looks more like the other problems, right? And then this would be like y of 1 equals -1. This one would be y prime of 1, right? I don't know, does that clarify it a little bit and sort of help to start? I don't know. What did you do when you started this one? And maybe your numbers are different, so I could pull yours up if you wanted to. Well, it's too late. Let's just start it. How do we do it? We're gonna do d over dx. What do you get for this one, John? So we should differentiate it first. What happens to the 9 when you differentiate it? Comes to 0. What happens to the 5y? Specifically, John, what do you think? I'm sorry? So y is a function of x, so it's going to become 5 dy dx. Right, we're doing d over dx here, and we're doing d over dx of y. If we did, which is just dy dx. If we do d over dx of x, that's when it becomes 1. Thoughts about that? Specifically, John, since you seem to be a little confused about that.
So the next one, 4x squared y.
Yep.
Cubed, so 8x.
So this is a product rule. Because we have an x squared multiplying something that is a function of x. Very similar to the last problem we had, where we had a product rule of x times y, right? It's the same as this thing we just did here. That was this product rule. So what does this one become? Got a product rule in that 5xy. I mean, let's see, 4x squared y.
So 8x.
Yep.
Y cubed.
Yep.
4 squared.
Mm-hmm.
And 3y squared.
Yeah, so but it's a chain rule, so it's 3y squared times the inside, which is y prime, or we've been writing it as dy dx. Right, so the y cubed part is the same thing in the last one as this piece. If we did 4y squared, it was a chain rule, and it became this. So it's the same kind of idea. It's that. Right, so that's this part right here becomes this part right here. Right, because it's not just a y, it's a y with some x hidden inside of it. It is a function itself, and you're differentiating with respect to the hidden part of it. So you have to, it's a chain rule in that respect. And I've run out of space, but it equals 0 on the other side. So what do you think about that derivative? I'm sorry? Okay. In the interest of time, I'd like to let you try to finish that one. It's the same process. Right? You would move this piece over to the other side because it does not have a dy dx, but these two do, right? There's one here and there's one here. So you subtract the 8xy cubed over, factor out the dy dx, you divide things over, and then you just plug in, what is this one wanting us to do? Right, it wants us to plug in the number 1 at the end. Right, so this is telling us, you know, so the steps are number 1, just like the other ones, solve for dy dx. 2, you plug in x equals 1. And this is telling us when x is 1, y is -1. And that's what this piece is telling us right here. Other algebra sort of things there? Seem okay? Algebra-wise? All right. I'd like to keep going and finish off this L'Hopital rule section. And with just one more page in it, bring that up. So remember this idea, and this is in the homework that's due next week. It says, hey, if you try to do these limits on the left that I've got boxed in yellow, if you try to do these limits, either infinite limit or just a regular limit, and you get an indeterminate form, remember that's either 0 over 0 or infinity over infinity, then you can move forward in these limit problems by taking derivatives. Right? The thing on the right says, hey, if you run into this problem, try taking derivatives of the top and the bottom and then evaluating the limit again, because it turns out that the ratio of derivatives is the same thing as the ratio of the original function in terms of these limits. And so we saw that in a couple examples, right? Like I'll just sort of run through this last one that we did. This particular function was approaching 0, x was approaching 0, and we saw that when you plug in 0, you end up with this indeterminate form. And so we applied L'Hopital's rule by differentiating, right? So from here to here, we did d over dx of the top and the bottom. We tried the limit again. We still got a indeterminate form. And so we applied the L'Hopital's rule again, right? So from here to here on the bottom, we differentiated again. And at that point, when we plugged in 0, we didn't get an indeterminate form. Like that was okay. And so that's how we evaluated that limit. So, you know, I was getting at the idea that sometimes you have to do it twice. And so we're just going to apply this to a slightly different situation in this last page here. And I think I'll probably stop there. I prepared a couple things, but how are we doing that time? There'd be enough time for this quiz. So yeah, we'll probably just finish this and start this thing on Monday. So this second page is just a slightly different flavor of the last page. So it's saying, hey, what happens if we have a 0 times infinity form? Well, it turns out we can rewrite it so that it looks like this. And before we do that, I wanted to remind you of a few key things. I don't know, reminders is what I'll call them. Number 1, if you have something that looks like 1 over 0, you want to think about that as being infinity, right? 2, if you have 1 over infinity, you want to think about that as 0. Now, infinity is not a real number, and so these are just like hypothetical, kind of like generalizations of this idea, right? When you have 1 over something that's really, really big in the bottom, that's getting bigger, it gets close to 0, is what I'm saying. So there was a mathematician in the room, they might get mad that I wrote something that says 1 over infinity equals 0, so just want to clarify that. The other thing we should be a little bit remember about is what the graph of natural log looks like, since it's in the first problem. And natural log has an asymptote right here, and does this, right? And so the reason I want to point that out is because in the first problem, we're going to plug 0 in. And so ln of 0 is negative infinity, just looking at the graph, right? In other words, you can't plug 0 into natural log because there's an asymptote there, and the function itself is getting close to negative infinity at 0. So anyway, I just wanted to remind you of those 3 things because we're going to kind of use these ideas in these problems down below. And I'll kind of reference back to those 3 things. I'm going to clarify something about what I'm trying to say there. Just remember those things there. Okay. So how's this first problem work? Myself here. Yes. So we're doing the limit as x goes to 0 of x times natural log. And so notice if we just plug the 0 in, right? You always want to plug the number in with these limits, just see if it works. If we plug the 0 in, we'd get 0 times negative infinity, because like I just said, natural log of 0 is like negative infinity. And so this is one of the other kinds of indeterminate forms. And since I've got this whole document here, I think I will just slide up to that real quick. But I wish, can I do this? Move this and then do this. Still trying to get the hang of this. I thought that thing came out on the side. All right, I'm not going to do this. John, you're an iPad whiz. How do I get that side thing to come up? I know, sometimes it comes out and sometimes I feel like it just doesn't. Don't know why, because then I could just scroll better. Anyway, I'm not going to waste our time with that. This is one of the other indeterminate forms. Sorry, I just made you all dizzy by scrolling for a second. But 0 times infinity, if you remember, if you scroll back up to one of the original pages we looked at, 0 over 0 is not good. Infinity over infinity is not good. 0 times infinity is also not good. That was one of the other things. Like, what does that mean? Is that infinity? Is that 0? Or we have these other kinds of indeterminate forms. This is one of them. But the thing is, we can actually rewrite this idea to make it look like either 0 over 0 or infinity over infinity, right? So what I mean, let me just kind of show you and then we can talk it through. But notice that our original function can be rewritten like this. Right, so I just take the x and instead make it 1 over x and divide, right? Because if you were simplifying that, you'd flip the thing on the bottom and then multiply it, right? And if we did this limit as x goes to 0, right, in ln of x is infinity, and 1 over 0, because of the reminder at the top there, is also infinity, right? So this would be like an infinity over infinity thing. And so we can take our original function and just rewrite it like this to make it look like the right indeterminate form, and then we can use L'Hopital's rule as the idea. Right, so it's a bad indeterminate form that we're rewriting into a different bad indeterminate form so that we can apply this property, right? Because now we have this situation, and so we can just take a derivative. That's sort of the idea. So let me just pause there and let people finish writing that down and see if there are questions about what I'm trying to say. Anything else? So it's like an algebra trick. It's nothing groundbreaking. It's not the kind of thing that I can't even recall if I put these kind of things on the test. It's just like a nice thing to know about. And there are some in the homework that look like this. All right, so let's do this problem. This is kind of the scratch work. Let's do the actual problem. Are there questions about the algebra, what I'm trying to say there about rewriting this thing? It's okay to be confused about algebra. Jeff, go ahead. Yeah, and I see Sebastian's asking, please explain. Yeah, do we do one of those actually? Let me see here. Oh, can you have 0 over infinity? Is that what you said? So anything 0 over anything is 0. Okay, and especially 0 over infinity, because we just said up here that 1 over infinity is 0. And so 0 over infinity is like extra 0 or something like that, right? Because 0 over infinity would be, you're taking the number 0 and you're dividing it by something huge. And so it's like not only 0 from the dividing by huge part, but it's also 0 from the numerator part. Yeah. I thought you were asking about, can you switch these things into 0 over 0, which you can also do. And I was trying to think about whether I did that. We're going to do that actually on the next one. But I also see Sebastian asked about this idea. So this is getting at the idea of when you have something like this, you rewrite it like this, right? This thing flips over and multiplies. And so if you have ln x times 1 over x, that simplifies by being this, right? Which is just x ln x. And so usually, you know, the way we usually see these things is you end up with something like this that's ugly and a problem, and then you simplify it into something that's not ugly. But what we're doing is the opposite. We're starting with something that is in the wrong type of indeterminate form, and we're going the other way to rewrite it in an ugly compound fraction kind of way, but that gives us infinity over infinity. That's sort of the idea there. So explain it, Sebastian, or anyone? It's the property of dividing by a fraction. Okay, I'm going to delete this stuff to finish this one off. Oops, that's too much. Okay, so let's finish it. Again, this is all just scratch work so far. Let's actually do the problem. So our original problem said this. We didn't really know what to do. It's an indeterminate form, but we're going to rewrite it so that it means the exact same thing algebraically. It just allows us to use L'Hopital's rule. Right, this is now in the correct form, right? And do you remember how we're going to differentiate things in a second? What do we do with 1 over x when we differentiate it? Remember that? Yeah, it's x to the minus 1. You could do a quotient rule on that if you really wanted to, but the easy thing we talked about doing was just thinking about it as x to the minus 1 and then doing a power rule, right? But so now it's in the correct form. We're thinking about this as x to the minus 1, so we're just going to do L'Hopital's rule. So I'm going to apply L'Hopital's rule, LR, just like we have in the past, which means differentiate. And so when we do d over dx, ln becomes 1 over x, right? That's the derivative of ln. And then x to the minus 1 becomes bring down the power, subtract 1 off the power. And it's good that Sebastian clarified that fraction thing, because we've got a compound fraction again, and it's going to simplify in a way that makes this work. So let's keep going with this. Is a derivative okay? So let me just maybe clarify in case it's not clear. When I say apply L'Hopital's rule, we did d over dx of the top and the bottom separately. Right? ln becomes 1 over x, x to the minus 1, power rule. The rest is algebra, so that's okay? So let's just simplify it. So right, so this really looks like this. And this is the same property we were just talking about a second ago. You've got a fraction divided by a fraction. You take the one on the bottom and you flip it upside down and you multiply it by the one on the top. And you can see when we do that, nice things happen. It's going to work out very nicely here. So we'll have the limit as x goes to 0, 1 over x times minus x squared over 1. just becomes minus x. Right, the x in the bottom canceled with one of the ones on the top. And you can plug a 0 in there and just get 0. And that's the answer. What do you think? Anything? All right, I'm gonna let you try the middle two here. I think the middle two, is that right? The middle two are from the last idea. I'm just gonna show you the one on the bottom here before we do the quiz here. So the one on the bottom is an infinite limit, right? The one on the one we just did was approaching 0. The one on the bottom, we're plugging in infinity. And so if we think about plugging in infinity into this one, it's like infinity times sine of 1 over infinity, which is infinity times sine of 0. And sine of 0 is 0. And so this is one of those weird indeterminate forms, infinity times 0. And so we have the same kind of situation we did a second ago. We had 0 times minus infinity in the last one. But we can do the same kind of thing, where we just take what we have, rewrite it as 1 over x, and then we'll have 0 over 0 in that case. And so I thought this is the kind of thing that Josh was asking about before. And let's look at this one. So let's instead do the same thing we just did, which is to take the x and make it 1 over x. And so I should put an equal sign in there. So this is equal to this new step. We just took the x and we made it 1 over x. And put it in the bottom, right? And then when we do that, it becomes 0 over 0. If we plug in the infinity now, we'd get 0 over 0. And so now it's in the quote unquote correct bad form, I guess is the way to think about it, because it's a compound fraction that's still indeterminate, but now we can apply L'Hopital's rule. Right, and this one, the bottom's the same situation. We've got x to the minus 1, but the top is a chain rule. So let's do it. So we're going to apply the rule again by doing d over dx. And how does this look? I don't know how much detail you guys want to see about these. I'm kind of hoping at this point I can just write this. So the bottom stays the same as last time, right? It's going to be this. The top is a chain rule. So sine becomes cosine. And then you multiply by the derivative of the inside, which is the same thing we just did a second ago. Happy to show those details if you want to see it, but let's just finish this one off, because notice how you got the same thing on the top and the bottom, right? There's a minus x to the minus 2 here and here, and so they just cancel right out. So this actually has a nice little property that lets us get right to the answer after we do that. Right, because now if we plug in infinity, and plugging in infinity is still a little bit of a misnomer. You can't really plug in infinity, but hopefully you get what I mean. Right, it's cosine of 0. Cosine of 0 is just 1. That's no problem. Should I go into more detail on those derivatives? I don't mind doing that. Oops, that's not what I meant to do. Let me just let everyone write that down and see if there's something specific you want to look at. Do you want to see the chain rule one? Does that seem okay? I'm just gonna, I feel like someone always asks me about this, so I'm just gonna do it right here. When you differentiate sine of 1 over x, it's a chain rule with the outside function being sine and the inside function being 1 over x, right? And so that's why when you differentiate this, it becomes cosine. But then you want f prime with g plugged in, and so you get cosine of 1 over x. Remember, so you kind of ignore what's on the inside, you just differentiate the outside piece, so it becomes cosine. And then the inside piece, when you differentiate that, we've done that a couple times, that's where you bring down the power, subtract 1 off the power. Right? So anyway, people usually ask about that piece, so I thought I'd throw that in there. And so that's how we get this part. But the cool thing is it cancels with the bottom, right? So that just like was really nice, and then we move forward. All right, what do you think about those? Horrible, not too bad, not too great. All right, I like that. It's not too bad. What do you hate? Well, we just got back to 1 here, right? At least it's like a nice number and not something you're like, is that the right answer? It's not too horrible. That's great. Just a little bit horrible. It is horrible, but not too horrible. That's a fine way to think about that. I don't care. That's great. Yeah, I don't think we did this in my last pre-calc class, but I feel like this always comes up in my pre-calc class, or someone always says like, oh, it's not too bad. And then that just ends up being like a really great thing. Like, oh, it's not so bad. We can do this. Just a little bit bad. Anyway, let's finish off these last couple. And I was going to ask you to try them. These are both what I would consider quote unquote easy type L'Hopital rule problems. They're already in the correct form. So if you plugged in 2 in this one, you'd end up with 0 over 0. And you can just take my word for it, right? You get 8 minus 8 in the top, and then the bottom, you'd end up getting 20 minus 20. But anyway, all you got to do on that one is just start taking derivatives. And the same thing on the bottom. When you plug in 0 on that one, you would also get 0 over 0. And so there's no tricks to these 2 in the middle. We're just going to apply L'Hopital's rule. I will give you the hint, though. You have to do it multiple times on the one on the bottom. If I'm not, if I remember correctly, yeah. And more than twice, I think. So just take a second and try that. See if this makes some sense. The one on the top should be pretty easy, right? Just straight power rules until you get something that makes sense. And I think you only have to do it once on that one. So I'm just going to pause here and let you try those 2. Maybe I'll slowly start writing down answers here, just in the interest of time. Oops, what the heck just happened? Oh, now the thing's on the sides up. So the first one is not too bad, right? Should just be one application, but as we start to do the second one, we'll give you a little more time on that one. You have to do it more than once. And I think at least 2 or 3 times. Let me start writing out some of those details though. Keep working on it yourself here. Should I get -6 on that second one? So I'm reaching here. Double check my work here. Okay, that makes me feel good. Yeah, so that you had to do the second one multiple times. Maybe I'll start just kind of talking through it. But the nice thing is it never strays from being 0 over 0. So it's not like you have to do one of the things you did previously, which is rewrite it in some way, right? Starts over at 0 over 0. When you take the derivative, sign changes in the cosine, but then you end up with 1 minus 1. So you still get 0 over 0. And so you just keep having to take derivatives. It's still in the correct form is the kind of thing I'm trying to show you, right? All the things that got circled allow you to keep using L'Hopital's rule. If it changed to something else, we'd have to rethink it, but it's still 0 over 0 in all those cases. We do it again, we get 6 over sine, plug in a 0, it's still 0 over 0. But when we get down to this last spot, right, now there's a 6 in the top, there's no x's left. So it's not going to be a 0 in the top anymore. 0 in the bottom might be an issue. We might have to rethink that, but it doesn't happen. We get -1 and just end up with a -6. So we had to do it 3 times there, right? 1, 2, 3. Okay, this is what I've got. And so this homework is posted for next week. Probably do some quiz on this next Friday would be my guess there. Thoughts about L'Hopital's rule though? Any of the remote folks have any thoughts about that? Don't look too bad. That's what I like to hear. Pretty straightforward. Wonderful. Yeah, L'Hopital rule is not too bad. There are trickier aspects. We could sort of go deeper into it. I don't get too crazy. I just try to do not really the basics. I think this idea of taking 0 times infinity and rewriting it is definitely making it more complicated. But there, just know that you can always go deeper into some of these things. L'Hopital's rule is definitely one of the things that a little bit of a rabbit hole. It has other applications too that we're just not going to touch on. Anyway, so someone just asked, are all the cosine x's and the sine x's give you 1? Yeah, I almost mentioned this. If you're still having a problem with the trig, like, I would love to talk to you about that. I can only say that so many times, and I can't force you to do that though. But the thing that I almost wrote down was sine of 0 is 0. Cosine of 0 is 1, is the 2 things that come into play in that particular situation. And so that happened, all these places that became a 1, this one became a 0, that one became a 1, that one became a 0. So those are the ideas we use there. Anyway, I'd still love to talk to you about trig if that's something you want to review. I posted a bunch of stuff, never heard about it. Hopefully that helped. All right, what do we got? We got 20 or so minutes here. That's plenty of time to do this here quiz. I'm gonna start passing it out in person. If folks online would get situated, turn their cameras on, et cetera, I would love to pass it out to you too. Open note like always. And I will say something quickly about it after I'm going to send it through the chat, remote folks. So one thing I tried to do, let's see if I remote have it open. I tried to label the sides like on my iPad, and then when I went to print it, it didn't print out the labels for some reason. And you can see part B here says, list any constraints on the variables X and Y. So your picture should look like this. So if you wouldn't mind, everyone, including people who are remote, you could just throw labels. So, you know, let me start over. This first problem is an optimization problem. I'm not asking you to solve it. I just want you to set it up and that's it, right? So determine the objective function, write down the constraints. In the situation, it's a box with a square bottom. And so that's why there's two X's on the bottom, because it's a square, right? And then the top, the height, might be a different dimension, which is Y. So in part B, where it says list any constraints on the variables X and Y, your picture should look like that. That's what I'm trying to say. Can I clarify anything else about that? No, I'm not asking you to solve this problem. I just want you to set up the objective function and write down the constraints. Okay. On the second problem, this is the implicit differentiation part, and they're both based on the same equation, right? So you have this equation that have X's and Y's in it. In the first problem, you should assume Y is a function of X and do d over dx, okay? In the second problem, you're gonna do d over dt and assume that both of the things have a t inside of them. And so that changes some of the rules you use. Hopefully you understand what I'm saying there. Basically, I don't know, I can't really say too much more about that. Let me know if I can help you a little bit, but that's my clarification there. And hopefully you've done enough of this homework to do well in this. I hope you do. Let me help if I can, especially folks online. I'll put my number in the chat here if you want to give me a call. And also just to clarify the second one further, I'm not asking you to solve for dy, dt or anything, like just do the derivative. You don't have to plug anything in, you don't have to isolate the derivative. I just want to see that implicit differentiation makes some sense to you. That's what the point of this is. Nothing to solve, no slopes of tangent lines, nothing like that. So maybe provide a hint for anyone who's stuck on the constraint part of that first one. By saying you have 10 square meters of boxing material, that means you want all the area of all the sides to add up to that amount, right? And the unit's meter squared because it's an area thing. So it's not, you're not squaring 10, it's, you have 10 square meters of material. So you want all this, the area of all the sides of the box to add up to 10. What's up, guys? Got my next class starting in a minute here. Everyone else has just left. I actually forgot you guys are still working on this. How's it going? Talking to Harris, Sebastian, and Tayshawn.
I still ain't finished.
Say that again.
I still haven't finished.
Can you please try to finish so I can start my next class?
Nah, for sure.
I'm on the last part.